Hello, I'm Professor Afshar at Glendale Community College. This is Physics 103, Lecture 23. In this lecture, we'll discuss the law of reflection. This topic is covered in Chapter 35 of our textbook by Surway and Jouet. Before turning to the law of reflection, we should spend a couple of minutes discussing how we visualize or represent waves. Back when we were talking about one-dimensional waves, like rope waves, we represented them using sine and cosine functions. Unfortunately, that representation is not adequate for two- and three-dimensional waves. For two- and three-dimensional waves, we need a better way of visualizing or representing them. You've already seen the wavefront representation. In the wavefront representation, we draw lines or contours that represent different parts of the wave, like its peaks or its valleys. A little more precisely, each contour, referred to as a wavefront, represents adjacent points with the same total phase. It turns out for electromagnetic waves, which we want to discuss now, a slightly better representation is the ray representation. In the ray representation, once again, we draw lines or contours, but this time the contours, referred to as rays, represent the direction of propagation of energy. So the emphasis here is on how energy travels or propagates in the wave. The rays end up being parallel to the wave velocity. Let's consider a couple of examples. Imagine you're looking down on a pool of water, and imagine you're generating waves by tapping your finger in the middle of this pool of water. As you do so, you generate ripples that propagate outwards. If you wanted to represent these waves using the wavefront representation, you would draw a series of concentric circles. Each circle would then represent the peaks or maybe the valleys of these waves. If you wanted to represent the same waves using the ray representation, you would draw a series of lines like these pink lines shown here. Each of these rays indicates the direction in which energy is moving. Each of these pink arrows is parallel to the wave velocity at a particular point in space. As another example, imagine you're looking down on ocean waves arriving at a beachfront. If you wanted to represent these waves using the wavefront representation, you would draw a series of horizontal lines. Each of these horizontal lines represents the peaks of the wave as they arrive on the beach. On the other hand, if you wanted to represent the same waves using the ray representation, you would draw, in this case, a series of vertical lines. The pink lines here indicate the direction in which energy is traveling. As the waves arrive on the beach, they carry energy along these pink vertical lines. The pink vertical lines are parallel to the wave velocity of these water waves. Although we have not proven it, it turns out the two representations are related to each other. In particular, the rays are always perpendicular to the wave fronts. So for example, if you look at this particular point, you'll notice that the rays and the wavefronts are perpendicular to each other. That's true at every point in this picture. It's also true at every point in this picture. If you look at this point here, the ray and the wavefront are perpendicular to one another. We now want to discuss what happens when electromagnetic waves encounter the boundary between two media. For example, what happens when light waves encounter the boundary between air and water as they go from, let's say, the atmosphere into the ocean. Generally, when waves encounter the boundary between two media, they can be either reflected or transmitted. So some portion of the incoming wave energy is reflected and some portion is generally transmitted. There is a third possibility. Some of the energy could be absorbed and held by the boundary, although that's usually a negligible amount, and therefore we won't consider it in our discussions. So we want to understand what happens to the reflected energy and what happens to the transmitted energy. We're going to represent this situation as follows. Here we have two media that we're labeling as medium 1 and medium 2. You can think of these as air on top and water on the bottom, or perhaps water and glass. The point is we have two media with different physical properties, and we want to consider what happens when electromagnetic waves travel from one medium to the next. We're going to represent the situation using three rays. These three rays are labeled as follows. The incoming wave is represented by the incident ray. So the energy of the incoming wave is traveling along line 1, and we call that the incident ray. Some of the energy is reflected, meaning that it stays in the original medium, and that energy is going to be propagating along line 2. We call this the reflected ray. Some of the energy is going to penetrate the second medium and propagate there along line 3. This ray is known as the transmitted ray. It's also known as the refracted ray. We'll discuss refraction in our next lecture. Note that I am using the ray representation of waves here, but of course you could also represent the same thing using wave fronts. You could represent the situation using three different wave fronts. These wave fronts here represent the incoming wave, so these are the incident wave fronts. These wave fronts here are the reflected waves, and these wave fronts here are the transmitted waves. In this lecture, we want to discuss the reflected ray. More precisely, we want to understand the direction in which the reflection happens. In our next lecture, we'll discuss the transmitted ray. Focusing now on the reflected ray, the law of reflection states that the angle of incidence is equal to the angle of reflection. It's important to understand how these angles are measured. We can represent the situation as follows. As before, we have two media, medium 1 on top, represented by the light blue region, and medium 2 on the bottom, represented by the dark blue region. The boundary surface between the two media is this horizontal line here. Notice that the angles are not measured relative to the horizontal line, they are measured relative to the normal line. The normal line is the dashed line that you see here. The normal line is always perpendicular to the surface or the boundary between the two media. So the normal line serves as the reference line for measuring angles. This might seem a little counterintuitive at first, but in the context of electromagnetic waves, and especially in the context of light waves, this is a very common practice. We measure all angles relative to the normal line. The law of reflection, which is a very simple equation, is simply stating that this angle here is equal to this angle here. Of course, you can also talk about this angle here. Once you know the angle of incidence, then you can say that this angle here is simply 90 degrees minus the angle of incidence. And this angle here is simply 90 degrees minus the angle of reflection. However, keep in mind that when we write equations using angles, we'll be using the angles measured relative to the normal line. Let's get some practice with the law of reflection. A beam of light is reflected from two mirrors as shown below. Two angles are given. Theta is 50 and phi is 110. Find angle alpha. So we have two mirrors. They are angled relative to one another, and the angle between them is phi, which is given as 110 degrees. We have a beam of light that comes in. The angle of incidence is given at 50 degrees. It reflects off of the first mirror, hits the second mirror, and then reflects off of the second mirror. We want to know what alpha is. Using the law of reflection and a little bit of geometry, we should be able to answer this question easily. First of all, the law of reflection says that the angle of incidence, theta, must equal to the angle of reflection. That would be this angle here. Since the beam comes in at 50 degrees, the angle of reflection must be 50 degrees as well. Note that we're measuring both of these angles relative to the normal line for the first mirror. Now we know that the normal line is perpendicular to the mirror. That tells us that this angle here must be 40 degrees. So that 40 plus 50 gives us 90 degrees. Now that we know this angle here, we should be able to figure out this angle here. After all, we have a triangle, and the sum of the angles of a triangle must be 180 degrees. If this angle is 40 and this angle is 110, then this angle here must be 30 degrees. You can see 30 plus 40 plus 110 gives us 180 degrees. We're now talking about the second mirror. Recall that the normal line is perpendicular to the second mirror here. If this angle is 30, then this angle here must be 60 degrees. So we can say that the angle of incidence for the second mirror is 60 degrees. According to the law of reflection, the angle of incidence must equal to the angle of reflection, and therefore we conclude that alpha is equal to 60 degrees. Applying the law of reflection to curved surfaces can be a little tricky, so let's do another practice problem. 3 beams of sunlight, all parallel to each other, are incident on a spherical drop of water resting on a surface. For each beam, draw its reflection. So for this problem, we're not required to do any calculations. We just want to know roughly which way each one of these 3 rays will reflect off of a spherical droplet of water sitting on a surface. Since the droplet is spherical, we'll represent it by a circle, and we'll assume that the center is over here. According to the law of reflection, the angle of reflection must equal to the angle of incidence. But to know the angle of incidence, we need to have a normal line, and to have the normal line, we need to first define the surface from which each ray is reflecting. We define that surface as the tangent line to the circle. So for example, at this point here, we'll draw a tangent to the circle, and we'll say that the first ray is reflecting off of this flat surface. For the second ray, we'll say that it's reflecting off of this surface, which is again tangent to the circle at that point. And for the third one, it's reflecting off of a vertical surface because we're drawing a tangent to the circle at that point. Now that we have the surfaces defined, we can define the normal lines. Remember that the normal line is perpendicular to the surface. Now that we have the normal line, we can meaningfully talk about the angle of incidence and the angle of reflection. For this first ray, the angle of incidence will simply equal to the angle of reflection. If we had a protractor, we could measure this angle here. We would find that it's theta sub I. And then we would draw the angle of reflection going off at an angle that is equal to the incident angle. We can do a similar thing for this beam down here. Here, this angle is the angle of incidence. If we could measure this angle using a protractor, then we could easily draw the angle of reflection as being equal to that. For this middle beam, the situation is a little trickier. Notice that this middle beam is aimed directly at the center of the circle. What that means is that the angle of incidence in this case is simply equal to 0 degrees. In other words, the incident beam is traveling along the normal line, so the angle between the normal line and the incoming ray is 0 degrees. What this means is that the angle of reflection will also be 0 degrees, so in this case the reflected beam will simply go back out the same way that it came in. And that is the end of this lecture. Thank you for your attention.